I will briefly introduce him. The Professor Gogotsi is a distinguished university professor, and Charles Key Ross M. Bach, Professor of Materials Science and Engineering at Drexel University. He also served as director of the A.J. Drexel Nanomaterials Institute. Professor Gogotsi's research group works on 2D carbide and nitride called MXene, nanostructured carbon and other nanomaterials for energy, water, and biomedical applications. He has published more than 600 journal papers. His work on MXene alone has produced more than 80 invention disclosure already. He is also a fellow of many academic communities such as AAAD, MRS, RSC, American Ceramic Society, and so on. He also received a lot of excellent awards. But short time, just with that, I would like to welcome today's presenter, Professor Yuri Gogotsi.
Thank you very much for the invitation. Thank you very much for a kind introduction, Dr. Jung. Can you see my screen?
Yes, we can see it very well.
Wonderful. I just wanted to add also that I am affiliated with KAIST as a Jung Professor of Chemical and Biomolecular Engineering. So pretty much I'm speaking at an event organized at an institution I'm affiliated with. And it's also very unusual COVID time. I'm speaking from the United States. It's 23rd of September in the US. It's already the 24th in Asia. So I'm giving a talk on 2 days at the same time. And topic of my presentation will be two-dimensional carbides and nitrides of earlier transition metals known as MXenes. Those are the structures you can see on the cover of this book here. So before I moved over my presentation subject, MXenes, I just wanted to mention that for quite a few years already, we have been working with colleagues at the National Nanofabrication Center, which is located on the campus of KAIST, and several other universities in Korea, sending every summer students, undergraduate students, graduate students, to perform research in Daejeon. And of course, some of the results I'm going to show to you today come as a result of collaborations with outstanding Korean colleagues. So what are MXenes? Why do we care? You have already heard a number of presentations about two-dimensional materials in this conference, something that many believe are the building blocks of future technologies, future devices, future materials. When we use two-dimensional sheets to assemble structures with properties that don't exist in nature, not available in any single material. And of course, graphene has been leading the way, attracting attention of community to well-known earlier materials like hexagonal boron nitride, transition metal dichalcogenides, but also resulting in discovery of new two-dimensional materials like black phosphorus, silicene, germanium, making two-dimensional metal and covalent organic frameworks here. And among those new materials discovered after graphene were 2D carbides and nitrides of transition metals here. So why are 2D, why they're interesting? They're interesting because they give confinement of electrons in 2D space. They offer high specific surface area, many other interesting properties. And now we know that materials that don't have simple van der Waals bonded layered precursors, like for example, these ones, can also be made in a two-dimensional state. So MXenes are this type of materials, for example, titanium 2C shown here. So what is important usually in 2D materials? They have exciting electronic properties. Because of this two-dimensionality and confinement of electron in this 2D space, they can offer a variety of properties. But majority still of materials are either insulators like oxides or semiconductors. Even graphene, a zero band gap semiconductor, in fact, with a low concentration of carriers, but they also offer 2D materials flexibility, surface accessibility. They can be printed from solutions. They're basically very convenient blocks for building flexible wearable devices here. And their properties tunable. There are already a couple of hundred of those materials available here. And we added to this family many more, as this editorial in ACS Nano published a year ago shows, and actually very good starting reading about MXenes here. So we take transition metal carbides of those elements marked in blue. We connect transition metals with layers of either carbon or nitrogen, and boron is being considered at the moment as well. And on the surface, we can have a variety of other non-metallic elements, so known surface terminations, making MXenes. What is interesting? I already mentioned that we have many dielectric and semiconducting materials. Majority of MXenes studied so far are true metal conductors. Excellent conductors with high density of states at the Fermi level and high concentration of carriers. So they may really be the missing piece of the 2D puzzle when we now have pretty much materials with all electronic properties needed to build the future technologies here. So how do we make those materials? A colleague of mine, Professor Michel Barzoum at Drexel University, is the father of the field known as MAX phases. It's basically layered carbides and nitrides, where layers of transition metal carbides of nitrides are connected by these red atoms, layers of A element from this group, like silicon, aluminum, tin, or others. So these materials are layered, but there are strong metallic or covalent bond between them. And if you take an acid, you can dissolve this metal, for example, aluminum, releasing two-dimensional states and initially making something looking like thermally extended graphite or vermiculite clay, which are basically now layers of carbide with weak bonds, hydrogen van der Waals bond between the layers because the surface gets terminated by oxygen or OH. And this is how, working with Professor Barzoum and our student Michael Naguib, we produced first MXenes and published it in 2011. There are other ways to make MXenes. For example, it's possible to start from layered carbide, which are not MAX phases. For example, aluminum carbide layers connecting zirconium or hafnium carbide layers here. It's possible to use molten salt alkaline solution, do also electrochemical etching to produce these MXenes. But what is important at the end of the day, we end up with single layer flakes of carbides, nitrides, carbonitrides of transition metal with a variety of properties here. Moreover, we can really exercise engineering of materials at the atomistic level with this approach. You can see here some of the typical representative of material from this family. For example, they come in M2X, M3X2, M3X4 structure. Again, M stands for transition metal, X carbon and nitrogen. But we can make solid solution. We can mix randomly either different M metals, making, for example, titanium vanadium carbide. Or we can mix X atoms and we can make carbon nitrides. Moreover, we can push engineering a level further. We can make materials from one transition metal, for example, moly is on the surface, another one, titanium, is in the middle. This is so known out of plane ordered MXenes. Or it's possible to make MXene when there are alternating atomic columns of different elements, and if you etch away one of them, you end up with in plane ordered divacancy MXenes here. And this is only the beginning. More than 30 of this type of structures have been produced already. And earlier this year, we published in ACS Nano an article in January issue of SES Nano showing that it's possible to add also structures with 5 layers of transition metal, 4 layers of carbon, making, for example, this carbide moly 4 vanadium C4 with a herringbone layer structure. And this is certainly far from the end. Moreover, about 100 of simple stoichiometric MXenes are possible. With solid solution possible on both sides, the number of materials in this system is virtually infinite. And it's still not the end. We have the surface termination at the end. Usually we have oxygen, OH, some fluorine when we do etching in aqueous acidic solution. But when you use molten salt, for example, chlorides and bromides, the method developed in Ningbo initially and further pushed by Dmitry Talapin's group from University of Chicago in this paper published in Science about a month ago. It's possible to make bromine chlorine terminated MXenes. And bromine chlorine can be replaced with oxygen, sulfur, selenium, tellurium, amino groups, or surface termination can be removed, making basically non-terminated like electrolyte type structures MXene. So we have another level of control of chemistries of materials. You can only imagine what a variety of properties can be achieved, for example, by making sulfur termination instead of oxygen on the surface of niobium carbide. They demonstrated superconductivity in those materials. Things here. And the discoveries keep coming. Just in 2020, and we are only in September now, we showed an additional group of elements, group of MXenes with 5 layers of transition metals. Synthesis of MXenes by etching organic solutions was shown by Professor Barzoum's group. New general Lewis acidic etching route for preparing MXene was proposed by Qin Huang from Ningbo. And I just showed you paper from Dmitry Talapin on variety of surface terminations here. And the system of carbides and nitrides in 2D can grow further. Huimin Chen, who already talked at this conference, and Wen Tsai Ren from the Institute of Metal Research in China, published in Science about a month ago, a little bit more, August 7th, a paper on CVD synthesis of molybdenum nitride, which is not really exactly MXene structure, but again, 2-dimensional nitrides here. So it's truly exciting because development of technology has been really driven by availability of new materials. Whenever we have new materials, we can do something new which could not be done previously here. But of course, the key point is not just make new materials. We have already quite a few, but make materials with different properties from available today. For example, like metallic structures. Second, also learning how to precisely control those properties through structure, composition, and processing here. So what you see here is the density of state of titanium 2C MXene with no surface termination, and you see high density of states at the Fermi level. The electronic structure change if it terminates surface with fluorine. And if you bring oxygen on the surface, which pulls 2 electrons from each titanium atom, it's possible to open band gap, and actually wider band gap have been predicted for several other carbides. And we can heat samples of MXene with different surface termination in vacuum, changing their resistivity, and actually sometimes switching from semiconductor-like behavior, so resistance increasing with decreasing temperature, to metal-like behavior by simply removing surface termination, removing intercalated species from those materials. And in a very similar way, we can change the work function in these materials. For example, when we heat sample of titanium carbonitride MXene to high temperature initially, the work function increases from about 4 to over 5 electron volts here. And because we remove OH groups. And then we heat further, we start losing fluorine, and actually it goes back. And it's a very good agreement with theoretical prediction suggesting that OH groups take work function to about 2 electron volts, and oxygen terminated titanium 32 MXene will have about 6 electron volt work function here. So again, we learn how to control properties through surface chemistry. So what are those key properties which make MXenes useful, which make MXene really new addition to the family of 2D materials? First, as I mentioned, high metallic electrical conductivity. For example, in multi-layer films like this, with a lot of junctions, a lot of flakes, we get currently about 20,000 Siemens per centimeter, at least an order of magnitude higher conductivity compared to, for example, reduced graphene oxide. Here you can see single flakes, for example, it's about 20 micron long, single layer flake of titanium 332. And actually it's possible to keep it in solution processing such large flakes. You will never get moly S2 of that size through solution processing or oxide of any kind here because of very high mechanical strength and modulus of these materials. And they are transparent in thin films, very good for transparent conductors. They have hydrophilic functionalized surface and also absorb efficient electromagnetic waves. But what is important, we have again more than 100 stoichiometric MXenes predicted, more than 30 already reported, and virtually infinite number of solid solutions, so we can control, tune those properties here. So basically, if you compare it to graphene, you will see they are hydrophilic, water soluble, like graphene oxide. But unlike graphene oxide, they are conducting. Moreover, they're actually more conducting than reducing graphene oxide, which is used as highly conducting additive, for example, in batteries that Professor Yang Horn just was talking about here. It's also stiffer, stronger than both of those materials, thanks here. More transparent at the same thickness, and also comes actually in a variety of different colors and properties that tunable through surface termination, other things here. But of course, for new materials, there are always challenges. For example, there are many two-dimensional materials. Only a handful of those can be produced in any significant quantities. How to process them into films, fibers, print patterns, make devices? Are they environmentally stable? Because carbides, nitrides are non-oxide compounds capable of oxidizing in air. And we have been addressing over the past decade those issues one by one. For example, we have a reactor designed for us for synthesis of MXenes that can make 50 to 100 gram in a lab. And Murata in Japan has already 1 kilogram pilot reactor for synthesis at larger scale. So we get basically a powder looking like that can be, after the dissolved, brought in solution. And this solution can be processed very easily into films. For example, this is about 10 centimeters thickness and about 1 meter long MXene film with a thickness of just 1 micron. It's stronger than aluminum foil, and it has 15,000 Siemens per centimeter conductivity. No binder, no any kind of additives, just large MXene flakes holding to each other through hydrogen bonds and van der Waals bonds. So why can we dissolve it and fairly easily eliminate it? Because MXenes have high specific surface charge on the surface. Zeta potential in solution is typically between -40 and -80 millivolt. So this is a repulsion of particles in solutions. And you can see several different MXenes, you can judge by different colors, being dissolved in water when a droplet of concentrated solution is dropped into water here. And naturally, then we can produce dilute solution of single layer flakes. Those are 1 liter bottles of MXene flake solutions. And as soon as you have a solution, colloidal solution, or liquid crystalline solution that we used to make, for example, film shown in a previous slide, you can process them from aqueous dispersion. Moreover, again, let me repeat, no surfactant on binder needed. So we have environmentally friendly and very easy process, and we won't have to burn off binder and surfactant, unlike in case of using metallic particles here. And that can be inkjet printed, screen printed. We can write, just fill your pen with MXene, or of course do 2D or 3D printing here. That's very important because it's easy to produce films. We don't know yet how to make wafer scale films of single crystal MXene by CVD. By assembling flakes into monolayer films with just overlapping flakes, it's possible to make like a pseudo monolayer films. And this work actually done together with Sung-Go Kim and Chon-Min Koo, two Korean collaborators. And then it's possible to pile up layer after layer and study the effect of the number of layers on properties of this material. Also, in earlier studies, it was shown that MXenes can oxidize in air. And while in assembled film, they have stability for at least several years. We have films which were made years ago, and they still keep their properties to a large extent. Single layer flakes could not stay in water for more than a week or two, or refrigeration, deep refrigeration was required in or transfer to non-aqueous environment. We showed that by improving structure, it's possible not only increase conductivity, but also keep titanium carbide MXene, for example, with virtually no changes you can see from Raman spectra for months at room temperature in water. Moreover, even after 10 months storage, single layer flakes, you will only see a few pinholes. They're circled here in red, otherwise you won't be able to notice it in this few micron flakes. No oxide at the edges, no oxide at the surface. So it's also possible to make these materials with good environmental stability for transportation and processing here. And we do process actually all of them in aqueous environment things here. And this was my goal basically, to introduce you to this variety of new two-dimensional materials in MXene system. And I'm going to speak only very briefly about few applications. Of course, nanomaterials are widely used in energy storage. You just have talk and we'll listen to another presentation from Professor Paul Levisatas about nanoparticles here. And of course, they used, as we showed in this paper, was also Yitsui, who spoke at the conference earlier, in energy storage. We're trying to push batteries and supercapacitor to this point of space where we can have high energy and high power density. And again, it's possible to do if we have surface redox reactions which can be provided by two-dimensional materials. If we have electronic conductivity that can give us high rate, because basically charging battery quickly simply means running high current through a battery. So you really need metallic materials that can also experience surface redox to have high energy, high density storage. And not surprisingly, MXenes have already been explored in a variety of energy storage applications. I have no time, of course, to talk about them, but they range from electrochemical capacitors to all kinds of batteries, metal ion capacitors, and also what is important actually, passive elements. You may recall I showed you 1 micron thin, very highly conducting and very strong film of MXene, which can potentially replace current collectors in many devices here. And of course, if you make MXene battery, you won't need conducting additives or binders here. But what we need to do is to understand how ions behave inside. For example, modeling simulation done by colleagues from Oak Ridge National Lab and UC Riverside showed that lithium and sodium in aqueous solution will come close to MXene surface. There will be some charge transfer, while, for example, some other ions like magnesium, cesium will stay solvated between the layers. And if we take organic solvents, some of the solvent we consider to be very good for supercapacitor, for example, acetonitrile, giving highly conductive solutions. When used with lithium salts, will actually go between the layers of MXene, as long as lithium ions, separating the layers, decreasing the performance. But propylene carbonate, which leads to an order of magnitude less conductivity in solution, actually results in complete desalvation of lithium, and only lithium will be going between MXene layers, leading to significantly larger cyclical area under cyclical thermogram and significantly larger energy storage. So whenever we deal with new materials, we need to understand how to handle them. We need to look into their chemistry and electrochemistry here. But if we do it correctly, we can get some really exciting results. For example, I'm showing here cyclical thermograms for MXenes in sulfuric acid, basically protic electrolyte. And what you will see, at close to 0 volt, there is double layer type of a capacitive behavior. But at lower negative potentials, there is just wide redox peak overlaid on a double layer envelope here. Moreover, this behavior, redox reaction, is possible up to rates of 100, even 200 volts per second. So what does it practically mean? It's possible to have redox energy storage at enormous rate, millisecond time, as long as you have metallically conducting, highly conducting materials, because in most cases, we're really limited not by ionic, but by electronic conductivity of our electrode materials in zero. And this is a very important fundamentally. Second, also, MXenes have significantly higher density. This activated carbon uses supercapacitor. So in volume, when we talk, for example, about batteries or energy storage in general for wearable devices, for personal electronics, we can actually have, for the same gravimetric performance, we can have several times higher volumetric performance. But naturally, when we talk about 2D materials, we always think of flexible, wearable devices. For example, printed electronics, yarns that can be knit into textiles, making energy storage devices for textiles. And of course, it's possible to use this very high rate, as shown, for example, in this work done together with KAIST, with Hussam Al-Sharif. Here are 100 printed supercapacitors on a silicon chip, showing actually close to 90-degree phase angle and high frequency behavior, making them useful potentially for AC-DC conversion, competing with aluminum electrolytic capacitor with orders of magnitude smaller volume. And we also work with Professor Hoseok Park from SKKU to show similar or even actually faster performance for MXene conducting polymer nanoscale devices. And it's possible to make transparent supercapacitors. This is an example of work done together with Valeria Nicolosi and Johnny Kalman at Trinity College. And again, we get very nice performance volumetrically, and this device is transparent. Moreover, what is very important, we don't need ATO film. MXene itself provides the performance here. And we can take a liquid crystalline suspension of MXene flakes and draw fibers. This is collaboration with Deakin University in Australia with Joe Razal. It was published also just half a year ago in ACS Central Science, was on the cover of the journal here, making pure MXene fibers. So there is nothing else, virtually no additives. And you can see a CM image of this fiber here, and here is a roll with a fiber drawn. Or we can take a conventional cotton fiber, infiltrate with MXene, and again, build energy storage devices by knitting them into textiles here. And I can continue and go on and on, but just a few more examples of applications. Since when we charge MXene, we change its oxidation state. We also change its optical properties. We can actually, this is a UV spectrum of titanium 332 MXene. And you can see by applying about -1 volt voltage, we can shift the plasma resonance peak by 170 nanometers. So basically what we do, and it doesn't have an anodic potentials arranged here. What we basically do when we shift it here, we change the color of this MXene. It goes between green in normal state to blue when it's reduced state. So we can make an electrochromic device. And different MXenes, as you can see here, have very different colors. So those are just 5 different MXenes foils having different colors, and in solution, they will have complementing color. As I mentioned, those are plasmon colors and materials. And we can use them because of their conductivity and two-dimensionality for communication in antennas with very low actual attenuation, lower than some metals, and make again printable antennas, also even transparent antennas. Or we can print RFID tags. And of course, for Internet of Things, having 5G patch antennas, having RFID tags, and being able to print them from just aqueous solution onto pretty much every surface is of great practical interest here. And final couple of examples are related to another application in communication and electronics, electromagnetic shielding. And this work again was done with a Korean collaborator, Professor Chun-Min Koo. In 2016, we really changed the field of electromagnetic interference shielding by showing that materials with conductivity, a couple of orders of magnitude lower than copper aluminum, titanium 332 MXene, actually can reach the same level of electromagnetic interference shielding, protecting devices, protecting credit card, and anything else. Moreover, it's possible to achieve about 50 decibel. So basically 99.999% protection from electromagnetic waves with just like a 1 to 2 micron film of MXenes. Later, we showed that it's possible to get 20 decibel, which is sufficient for many applications, 99% of shielding, with just 40 nanometers thin film of titanium 332. And variety of other MXenes can be used. And of course, depending on their conductivity, they show different performances, but it's also changing non-linearly. So there's a lot of interesting science we're trying to figure out. And just about 2 months ago, we published another paper with Chun-Min Koo, actually really breaking all the record and showing that titanium carbonitride MXenes, which is actually less conducting than titanium 332 MXene, outperforms even copper films. And with very thin films, it's possible to achieve enormous, virtually complete absorption and reflection of electromagnetic waves. Moreover, the increase after annealing of titanium 332 achieved thanks to increasing absorption with two-dimensionality of this material here. Again, we're still working to fully understand the mechanism, but its fact that by itself is really exciting here and has also enormous potentially practical applications here. And there are many, many other applications based on properties of MXenes that I mentioned to you. For example, being conducting and transparent, they can be used as transparent electrodes in LEDs, flexible LED, organic LEDs. And this is again work with Korean collaborator Tae-Woo Lee from Seoul National University, showing pretty much the same behavior with ITO and MXene film. And keep in mind, those films we have today are still very, very far from perfection. Those really like a first step, first generation, second generation, maybe for titanium 332 material. We can push further, and they're flexible and don't have limitations of ATO here. It's possible to make gas sensors, and again, kind of a conceptual change. People used semiconducting materials as gas sensors and measure their change in conductivity, but they require heating. Metallic materials have not really been used for gas sensing, but because of high conductivity, we actually can get very high signal to noise ratio with MXenes and record a number of gases in the environment. And this is a work again done with KAIST and NFC with Hita and his group here. So basically, there are many, many different applications. Some people, like Hussam Al-Sharif from KAIST, start talking about an entirely new field emerging he calls maxitronics, because of such a variety of properties. Pretty much various kind of devices can be made using MXenes. And of course, even these numerous applications I already discussed, or at least mentioned. I would not say discussed because I didn't have time to go in depth here. Only a small part of what is possible. Transition metal allow, of course, catalysis and electrocatalysis here. MXenes are very efficient, among the most efficient light to heat transformer. And again, since plasma resonance is achievable in visible or infrared range, depending on composition, it's possible to tune it, use, for example, for destroying tumors by photothermal therapy. There can be excellent sorbents for biomedical and other applications here. They can be used in membranes for water filtrations here. And many interesting optical applications, from surface enhanced Raman spectroscopy to lasers, photonics, plasmonics, and I briefly mentioned electrochemical devices here. So I hope you got at least a flavor of this new emerging family of materials. If you want to learn more, you are most welcome to join the third international conference on MXenes, which will be organized in Ningbo. It's a hybrid conference, so if you're in China, you can attend in person. From elsewhere, you can listen to presentation online. We're organizing with Professor Qin Huan from NIMTE. And this is actually my very last slide. I would like to acknowledge people who did all this work. This is my research group, not this summer, because of the COVID, we could not have our annual summer party. It was taken last year. But really, of course, students, postdocs, current, former visiting scientists are the people who do the work. But we also work with many excellent collaborators in the US and abroad. And I listed in red several of collaborators in Korea. This list is not exhaustive. There is just not enough room for everyone here. But of course, exploring so many different materials, so many different properties and application is impossible without collaborations. And thanks for many funding agencies, including National Research Foundation of Korea, for supporting this research here. And with this, I'm going to stop, and I will be glad to answer questions. Thank you.
Thank you very much for a very impressive talk, Professor Gogotsi. I'm very surprised by the very rapid progress in this new material system. So we have so many questions in our Q&A chatting board. So let me select a few of them. First question is by Kim M. Thanks for the great talk. I have a question. MXenes are known as energy material. However, it is proven that MXenes could be degraded in water. So this may have a negative effect on long-term performance of battery using aqueous electrolyte. What do you think about this problem?
Basically, I showed a slide. It used to be the fact. We know that it's not a fundamental problem. We know that surface good stoichiometry and surface oxygen can protect MXenes. So these flakes have been a single layer flakes in water at room temperature for 10 months. When they are assembled in devices, we believe definitely lifetime of many years is possible. Of course, there are some other MXenes with lower stability, but again, I think it's a matter of optimizing the material, perfecting the structure, controlling the composition, and we'll have much more stable materials. Thanks here. And actually read questions myself. I hope everyone can see them here. And people ask about 3D printing technology. What would, for example, be the target for 3D printed MXenes? There have been several publications showing it here. Everything from sensors to thick energy storage devices would benefit from 3D printing. For example, to have high areal capacitance or capacity of devices, interdigitated electrodes can be 3D printed here. This is just one example of the application here. What are the design parameters to look into in the case of scale up of the synthesis. In general, it's a reproducibility and ensuring that whether we have 1 gram to 1 kilogram, we still have the same properties. We know it's scalable at least to kilogram. But what we would like to do is to decrease, for example, water consumption in washing the material. We want to be able to have less expensive precursors, max phases. For example, titanium carbonitride, titanium 2C, titanium 3C2 MXenes, made of very abundant elements, titanium and carbon. So if we find a way to have a low-cost, scale-up method for the synthesis, we will have a really great impact on the technology with these materials. Another question is related for MXene electrode with optimal structure that can be obtained, can help to achieve high energy density for industrial application without adding battery type active material. I think all depends on what level of energy density you're looking for. For example, yesterday many of us listened to Elon Musk talking about new batteries for Tesla and use of, for example, silicon for anodes. Silicon will give you more storage than MXenes can theoretically give. However, MXene can be used in this case as a highly conducting binder for silicon electrode. And we had a paper published with Valeria Nicolosi and her group with Jung, who was a postdoc there at that time, a former PhD student, showing that it's possible to combine MXene with battery material, as you call them here. So I think this will be a way to get better devices when we have highly conducting binder and we have high energy density material, like, for example, silicon in the anode here. Another question I see is MXene for nanomedicine application. There are many applications. I did not have really time to discuss them. We work on several applications from absorption of uremic toxins. Actually, check the current issue of ACS Nano, September issue. There was a paper there. To skin electrodes, epidermal electrodes, brain implantable electrodes with colleagues from the University of Pennsylvania. And there are numerous papers on photothermal therapy and also drug delivery with MXenes and theranostic approach here. So those applications are emerging to a large extent because of biocompatibility and lack of cytotoxicity of MXenes here. And my feeling is that I have used my time. Or can I take a few more questions, session chair, John?
Oh, yes, I think you can answer a few more questions.
Sounds good to me.
Thank you very much.
Then I will also take a question on transparent conductive electrodes in photovoltaics here. Yes, we published I co-authored, I would say, 2 papers on MXenes for solar cells with transparent conducting electrodes. This work was led by my former PhD student, Johan Dalagnis. He is on faculty at University College London now, and he continues exploration of MXene in that area here. And what makes MXene better MISL and performance materials here? We believe it's really two-dimensionality, discrete character, not continuous material when waves interact with layer by layer of MXene. But again, there is no theory explaining this behavior completely. Chun-Min Koo at KAIST is really a leading researcher, leading efforts to understand this behavior of MXenes here. How to modulate interlayer distance from angstrom to nanometer? Easy, because you can intercalate. For example, you can intercalate amines, tertiary amines with different chain lengths, and you can control it up to, say, 3 nanometer spacing between the layers has been demonstrated here. And I think there are probably more questions that I can answer here, but the mechanism of ion behavior and transport mechanism by selecting different solvent. Q, despacing affects the transport. Yes, despacing affects the transport, and opening the structure of MXene facilitates ionic transport. For protons, it's easy, they're small. Lithium is okay, but attractive would be to have aluminum, magnesium ions, multivalent ions, larger organic ions, and for those, you really need to open the space in MXenes here. And why there is no titanium 332 bottom-up controllable synthesis? This is a good question to people who are expert in CVD and PVD. Who, again, you have seen beautiful paper in Science published by Huimin Chen and Vincai Ren. They also published Moly 2C crystals, and there are several other groups produced 2-3 nanometer thin crystals, but no one really made wafer scale monolayers. I firmly believe it's possible. Not being an expert in CVD, PVD, I leave this work to people who know more than me about this process here. And the very last question I'm going to answer here is, can the fabric be laundered? We had up to 60 wash cycles at elevated temperature, mild washing cycles, but machine wash cycles simulated. And yes, it can be washed here. And at least titanium 332 in multiple studies from many groups on different continents showed no toxicity so far. So we believe it's still pretty safe to use it for direct application on skin. And again, thank you very much for all the questions. Let me just show my last slide. If you want to read more, feel free to access our website and papers there, or just email me, and I will be glad to answer further questions directly. My email here on the first slide. Again, thank you very much to everyone.